Hello, everyone. Welcome to today's live broadcast, Advanced Sensitivity and Resolution in Flow Cytometry Through Innovation. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots and sponsored by Beckman Coulter Life Sciences. Beckman Coulter develops, manufactures, and markets products that simplify, automate, and innovate complex biomedical testing. More than 275,000 Beckman Coulter systems operate in both diagnostics and life science laboratories on 7 continents. For more than 80 years, the company's products have been making a difference in people's lives by improving the productivity of medical professionals and scientists, supplying critical information for improving patient health, and delivering trusted solutions for research and discovery. For more information, please visit beckmancoulter.com. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please click on the support button at the top right of your presentation window or submit your problem through the green Q&A button lower left. I would now like to introduce today's speaker, Dr. J. Paul Robinson. J. Paul Robinson is the SVM Professor of Cytomics in the College of Veterinary Medicine and a Professor of Biomedical Engineering in the Weldon School of Biomedical Engineering at Purdue University. He received his PhD in immunopathology from the University of New South Wales in Sydney, Australia. He has given a large number of talks and presentations to student groups and community service organizations. He is also the immediate past chair of the Purdue University Senate. His research area has been focused on reactive oxygen species, primarily in neutrophils and cell lines such as HL60 cells. His lab is currently focused on mitochondrial function. I will now turn it over to Dr. J. Paul Robinson for his presentation.
Well, good morning, everyone, and thank you, Judy, for that generous introduction. I was asked by colleagues at Beckman Coulter to talk a little bit about the nature of the CytoFLEX instrument and why this instrument is a little bit different. And if you look at the vast majority of instruments that are out there for flow cytometry, they all do a pretty good job. In general, flow cytometry is at a very high standard, and we are very glad that so many companies are building really extra high quality instruments. So I would say that there are 4 essential feature differences in the CytoFLEX than other instruments. And what I propose to do in this webinar is to really focus on those differences, to try to explain why they're different and what advantages or they may have. So the detectors, they're different. The light managing technology is also different. The fluidics are different, and it also has multiple software side scatter options. So I'm going to talk about those features. The question that one might ask is, why do we care? In terms of detectors, 100% of other flow cytometers use photomultiplier tubes. Why do we care if an instrument doesn't use photomultiplier tubes? Because photomultiplier tubes have been used for 40 years, and they have some great advantages. And they're certainly extremely good at doing what they do. So one might argue that it's a good idea to stay with something that works. That's certainly a philosophy that many people might have. If we look at light manipulation, the traditional dichroic and bandpass system that almost all flow cytometers works very well. Also, fiber optics work well. So why would we change something that's so fundamental? And I'll try to answer that question. What about fluidics? A lot of flow cytometers, maybe not most, use a positive pressure system that works very well. It may not be so quantitative, but that is not really considered a major disadvantage. There really are no major negatives about the way current systems work. So again, you have to ask yourself the question, why would you change a system if things work well? And finally, in terms of side scatter, I would say that a greater majority of instruments probably take their side scatter signal off the blue laser, the 488 laser on most systems. And this works very well for blood samples, for cell lines, and for reasonable size particles. And so maybe there are some advantages to looking at alternatives for smaller particles. So as I pointed out, the CytoFLEX instrument changes a few things. The detectors are not standard. The optics, I would say, is not standard. The fluidics is not standard. And there are certain combinations of lasers, which I think are probably available on most, potentially on most instruments. But there are some slight differences in how the CytoFLEX does this. So let's take a look now at each of these systems. And I'll, first of all, focus on the detectors. So why did I say that the CytoFLEX is a little different? As you see on the left side, I put a couple of pictures up of photomultiplier tubes. The one with the glass case is pretty nice because it really shows you what's going on inside the photomultiplier tube. We probably don't use those in any current flow cytometers, but the principle of the photomultiplier is well known and works very well. And there have been lots of developments in flow cytometers over the years. And on the right side is, let's say, a more compact version, one that's probably pretty standard on most flow cytometers. So this is what we have on our flow cytometers. And the reason is because photomultiplier tubes are very reliable, very sensitive, and they work very well. If you look on the right-hand side, you'll see this tiny little device there. It looks a bit like a tin can, and that's an Avalanche photodiode. And so what happens in the CytoFLEX is that we don't have any photomultiplier tubes. We only have Avalanche photodiodes. So what's the big deal about Avalanche photodiodes? Well, there are a number of issues, and I'm not going to go into a great deal of technical issue in this webinar, but I have prepared some other materials that will be made available shortly that will give much more detail on each of the things that I'm talking about today. But APDs are incredibly efficient. And if you remember what quantum efficiency is, it's basically the number of electrons emitted divided by the number of incident photons. So this is around about 80% for APDs, compared to about 25% for PMTs. And so traditionally, we've avoided using APDs for a number of fairly good reasons. But APDs do something very similar to what PMTs do in that they amplify a signal. And as I said, I'm not going to discuss the process how that amplification occurs. But if you think in general terms of what an avalanche is, and if you see up there on the top right-hand corner, this is Arma de Blam, which has a huge block of snow up there, which you have to climb over if you're going to get to the summit. And I can tell you from personal experience of being in these places that an avalanche is pretty nasty. Once that avalanche starts, just from a very small signal, just kicking a little bit of snow, you can have an avalanche that has hundreds and thousands, tens of thousands of tons. And in fact, that is what happens in an avalanche photodiode. So the term avalanche is really very appropriate there when you think in terms of what is actually happening in the avalanche photodiode. So we do have this ability to take a very small signal and amplify it. The other advantage of APDs is that depending on the type of APD you use, you can get a very broad range of wavelength selectivity. And it's actually much broader than photomultiplier tubes. Photomultiplier tubes have a problem above about 750, 800 nanometers. But avalanche photodiodes are very sensitive above that range. So it is possible actually to design systems that cover a very broad range. So that's a reason for considering APDs. And a new generation of APDs has been developed, and these APDs are very, very high quality. If you can reduce the noise of the APDs, if you can increase the efficiency of the connection of the signal to the APD itself, and if you have very clean electronics, it is possible to use an APD. And so a little later on, I'm going to talk a little bit more about APDs and how they're embedded into the CytoFLEX system and why they work so well. So the other thing that is quite different in the CytoFLEX is the detection optics. Now, if you look at the top of the CytoFLEX system, and I'm now looking down on top of the instrument, you can see in the center there's a silver box, and that silver box has a cover over it. Underneath that are 3 fibers, and you can see them popping out at the top there and going to each of these purple, blue, and red circles. What's actually happening underneath there is that there are on some instruments a trifurcated fiber, or one with 4 fibers coming out, and those fibers, that cover is really there just to protect those fibers. There's nothing secret inside that box. It's just a protection for the fibers, and those fibers are now going to these places where the optics is managed in the CytoFLEX. Now, I want to talk a little bit about what this process is, what we call wavelength division multiplexing. And this is one of the keys to the success of why the CytoFLEX is so efficient, and why I've been really impressed with how this system works. I don't suppose a lot of you know what wavelength division multiplexing is, but every single one of you is probably using it on a daily basis and don't really know it. This technology was really developed in the telecommunications industry quite a number of years ago, a couple of decades ago. And the goal was going from the days when a telephone had a single line to a switchboard and then a single line to someone else's phone. That's a very inefficient technology. And the idea was, can you put more signals over a telephone line? And that's how wavelength division multiplexing developed. Now, over the years, this has been enhanced tremendously. And so it shouldn't surprise you to know that when you pick up your cell phone and you make a call, you're obviously not connected to any wires. I've sort of shown a wire there, but it's a sort of virtual wire. But when you make that call, you are talking to some kind of tower, and that tower is receiving your cell phone message, and then that tower is either communicating with another tower by radio frequency or a microwave dish, or it's very frequently communicating with a fiber optic. And down those fiber optics, the goal is, instead of having one cell phone message to go through, it's to have many of them. I don't know whether any of you have ever experienced dialing a number and getting the wrong number, or actually talking to someone and having an interference on the line, but it is possible in the phone system to get some confusion, but it's a very rare event because wavelength division multiplexing uses very sophisticated technologies to separate the frequencies of each phone call, and it uses a transponder. Sometimes we use the term mux there, but it's a transponder that takes those signals, converts them into a mixed signal, and then it goes through fiber optic, comes out the other end to another transponder, which now separates them back to those original signals. So that's how a cell phone works. So if we look at what's actually happening from a light management perspective in a flow cytometer, in fact, in the CytoFLEX, you'll see that what I've shown up here are just a bunch of colors indicating different wavelengths, perhaps, of fluorochromes, and they're going to a little box. Instead of calling it a transponder, I've used the term mux, and then they travel, in this case on a fiber optic, and they go to a place where they're demuxed, or another transponder, and they're then returned to their original wavelengths. And so the question is, how does the CytoFLEX do this? So I'm going to show you some details of actually what happens inside the CytoFLEX. I've sort of drawn a diagram here. You can see on the bottom left, there's input light. Let's say this is the fiber optic. It's coming through and it's hitting a mirror. And that mirror is bouncing all the signal back to another mirror. Now I've drawn multiple mirrors on the back here, but you can imagine that that's just one single mirror, but it can also be multiple mirrors. It depends on how complicated you want to make this device. You can see that the signal then is bouncing out, and there's a bandpass filter there, and I've just put some numbers on those. You'll see this one says 420, 450, 480, 520, and all I've indicated there is that some of this signal is going to go through a bandpass filter, and that bandpass filter is going to restrict what is being sent here. And these are going to the detectors. In a normal flow cytometer, this would be a photomultiplier tube, and in the CytoFLEX, this is going to be an APD. So this is a block inside the CytoFLEX, and I'll show you what that looks like in a moment. But this is the principle. So this is really a reflection. It's a mirror. It's reflecting everything. What that means is that it's rather efficient, that it's not blocking any signals. All of the light is traveling as far as it can, and the appropriate light is that you want to select is going through this bandpass filter. And I'll show you in a moment how you can just drop in a different bandpass filter in there. So let me show you this again in a slightly different form. So you can see on here, on the top right, that there's an optical fiber. It's going through a lens, and it's hitting a mirror on this side, and some of the signal is going through to an APD that says FAPD, just a fluorescence detector. And then some of that, the rest of that signal, what doesn't go through, is bounced onto a mirror. And then some of that goes to another detector, and you can see that it's bouncing around and around and around. So that's the fundamental technology that's inside the CytoFLEX. So let's look at one of those WDM blocks. So on the bottom of this, you see the actual block, and at the bottom of that, you see a blue arrow. I'm just indicating in this one that the blue laser light is coming into this block. And inside the middle of that block, if you notice, there are some smaller blocks that have colors on them. Those are actually holders, and on the bottom of those holders, there's a really tiny bandpass filter. That bandpass filter is only a few millimeters wide and a few millimeters long, so it's extremely small. And so you can see in this very small area, it's maybe 40, 50, 60 millimeters, 2 inches across, that there are about 6 different bandpass filters in here. And just above it, you'll see a diagrammatic representation of the same thing. So you'll see some above the bandpass filters going through to some detectors. So this is what I would call a wavelength division multiplexing splitter. Now, that's one type, but the CytoFLEX actually has 2 types. And I just want to show you this, and I will bring this issue up again in a little while when I talk about the different lasers and how those laser combinations can be controlled and manipulated. But in this, on the right-hand block, you'll see at the bottom, there are 2 arrows, and that is representing 2 fiber optics that are coming into this block. Now, on this particular one, there's actually only 1, but I'm diagrammatically showing you that 2 could come into this. But above, you'll see that there's a small bar in the center of the circle. I don't know whether you can see my mouse, but I'm actually pointing to the middle of the right-hand circle. There's a little bar there. What's actually happening here is that that mirror is split into 2. And so there are now 3 APDs on either side of that mirror, and 1 fiber optic is serving one side and a different fiber optic is serving the other side. And as I said, I'll come back to that later, because this is one of the fundamental amazing advantages that I see in this instrument, because it gives you an almost unlimited number of combinations that you can manipulate with just a very, very simple process. So let's, well, I will show you one more thing that's related to that. And this is the same diagram that I showed before. Well, almost the same diagram, but I've made a slight difference in this diagram. You'll see at the top there's a single fiber optic coming into it, but in fact this is where the split is that I was showing you. So I've just drawn a black line there that sort of, let's say, creates 2 separate mirrors. Instead of this mirror being 1 piece, it's now 2 piece and is blocked. And so now I can bring a second fiber into this system. So you can see the blue fiber, blue laser is coming from this one, the red laser is coming from this one. And on the left-hand side, you see the number 3. That implies that I now have 3 APDs, 3 detectors that are coming from this laser and 3 detectors coming from this laser. So that that looks like this works in as two WDM modules. Okay, so as I said, I'll come back to why that's important a little bit later. So the model there is that it's very efficient optical pathway. It's certainly, I think, the most compact system that I've ever seen. It requires an extremely small amount of physical space, and the distance from the actual detection of the particles to the detector is extremely small. And these bandpass filters are really, really very, very small. And the fact that you can stick any bandpass filter into any way WDM module, I think, is pretty nice. There's virtually an unlimited number of combinations depending on which laser that you select. So I've discussed the fundamental differences in detectors, the fundamental differences in the optical system, and now I want to talk a little bit about the differences that this system has in fluidics. So it's really not complicated at all. It again may well be one of the simplest fluidic systems that I've seen. There are a couple of flow cytometers that have extremely simple fluidic systems, and the CytoFLEX is definitely one of them. I've put a circle around this device in the middle. This is a peristaltic pump, and this is the way that the sheath fluid is manipulated. Now, I think that the most reasonable question that you could ask about using a peristaltic pump is, well, don't we know that peristaltic pumps operate by rotating a bar around a tube, and that creates pulsations? And I don't think there's anyone in the field of flow cytometry that would be happy with pulsations going through the flow chamber. And so it's a very reasonable question as to how do you dampen any potential pulsation. Now, I'm not going to discuss the details of how this particular pump is designed, but I can say that the way it's designed is a very clever technique to essentially remove pulsations from the fluid that is going through to the flow chamber. So that saves us from dealing with having to struggle with a potential pulsation problem. And from my experience, that this works very well. Now, the other question is, can you get stable flow? This is a very reasonable question to ask. And we know that in traditional flow cytometers, where we use positive pressure systems, we have very sophisticated pressure and fluidic control. If you just take a look at any of the, let's say, traditional flow cytometers that are on the market from every company, you'll see how complicated the pressure system and the control system is for maintaining that absolute pressure control in the sample delivery system, so that the hydrodynamic focusing is absolutely stable and that there's no change in the flow rate unless you change the system yourselves. So this table, this histogram that I'm showing here shows the same thing. It's very hard to see, but this is a plot of fluorescence versus time. And I've drawn a line across the screen. The black line is a straight line that I drew, and the red line is the change in sample number, or fluorescence intensity in this case, of particles going through the system. And so, you know, it's pretty clear that this is a very, very stable flow system. Now, this raises an interesting question, and I can't resist a little bit of education on this issue, because it always concerns me that when I'm talking to people about flow cytometry and quality control, I just don't hear something that should be fundamental on every single instrument. Every single sample that's run on a flow cytometer should be collecting time as a parameter. And there's absolutely no excuse for people not to have time as a parameter on every single sample that's run. And the reason is this has been known for 30 years. Jim Watson, for those of you who don't remember Jim is past president of ISAC and a person who has a very high reputation in the field of flow cytometry for many years. And in 1987, Jim published this paper that you can see here, Time a Quality Control Parameter. And the very point of this was that if you aren't measuring time, how do you know that the sample was run over a long period of time in a stable flow mode? The reason you know is because you're collecting this histogram in the top right-hand corner that I've cartooned there. And you would see this on a histogram, but you know, if you collect sample for, let's say it takes you a long time to run samples. So we're running some samples at the moment where we have to collect a very large number of beads. Well, it's not a huge number, it's 20,000 beads, but in a very dilute sample. And the sample cannot, for a number of reasons, be concentrated. And so it takes us about 15 or 20 minutes to run each of these samples. If you don't run time as a parameter, and the only thing you do at the end of 20 minutes is look at a histogram, you're really not going to know whether there was a small blockage or some change in the flow rate. So I really want to emphasize this from an educational perspective, that you really should be collecting time as a parameter. So let me move on to the last section, or the second last section, is it, of what I want to talk about, and that is the side scatter. And for some reason or other, Beckman Coulter called this VSSC, violet side scatter, I guess is what that means. And let's ask us a couple of questions about side scatter. What do we know about side scatter? So some very basics is we know that in general terms, the larger the difference in refractive index, then there'll be more light scattered by a particle. We also know that the more granular the particle is, the probability of getting light reflecting off those subcomponents increases. And that's why you see in this diagram that I put in the middle there, where you see granular sites, for example, that have lots of granules in them, and a very different arrangement of the nucleus. These granules are like subcomponents of the cell, and they scatter a large amount of light. We know that the amount of light scattered by any particle is proportional to the diameter of the particle, and it's inversely proportional to the wavelength of light used to detect it. So if we lower the wavelength of the excitation, we'll see increased side scatter of any given particle size. So if you use, say, 488 nanometer excitation as opposed to 405 meter excitation, you'll get a certain light scatter signal from each of those lasers. If you move to a lower wavelength, you will actually increase the resolution of small particles that can be detected. Now, we know that, and several people have published on this. Now, we also know that when you enter a medium of a different refractive index, and I've put a little prism there, that the light waves that are reflected by this different refractive index is inversely proportional to the wavelength of the light, and with the lower wavelengths having higher refraction than the large wavelengths. And we can all thank Isaac Newton for working that out for us. So if you now look at lower wavelength, that is, say, 405 nanometers instead of 488, you can see here some data collected on the CytoFLEX where really quite small particles can be resolved. And I'll show you in a little while how easy that is to do on the CytoFLEX. But the point that I want to make is that you can actually measure side scatter simultaneously from each of those lasers in a very, very simple way. And because of that, and because of the ease of measuring it, this I think is one of the interesting advantages of the CytoFLEX. So let me now lastly talk about the lasers and the configuration of the lasers on the CytoFLEX, because that certainly will impact how many signals that you can measure and which WDM modules you need to use in order to collect these signals. So there are, at the moment, I understand 5 possible lasers that you can put on the CytoFLEX, although only 4 can be put on the CytoFLEX at any one time. And these range from near UV, which is 375, through to what people commonly call a violet laser at 405, a blue laser at 488, a yellow-green at 561, and a red laser. And in the CytoFLEX, the red laser that's used is a 638 nanometer laser. So here's one laser layout that you can have on the CytoFLEX. This one shows the 405 at the front. Now this is at the top of the CytoFLEX and on the very front. Normally this area on the left has a cover over it, so you can't actually see this. Of course, you don't want to have lasers exposed, so this is completely covered. But each of these black blobs on the right-hand side and the one at the back where the red arrow is are the actual lasers. And on the top right-hand side, you can see how the lasers are, let's say, visualized into the fiber optic collection, fluorescence collection that comes out of this system. And this is a single fiber that collects all of these separated lasers. So this is one configuration. There are several different configurations. So what I've tried to show here is a different configuration, and on this one I want to come back to what I said about these WDM modules, and and how these WDM modules can be applied. So you can see on the left here, one WDM module has several detectors and some bandpass filters up here. The middle one for 561 has the same sort of arrangement, but on the right-hand side, we have this split WDM module. You can see that two lasers, which let's say not the lasers, the light coming from the excitation of two different lasers is coming into a split WDM. And so that where the red circle is the WDM module that is split now. And a couple of things you see here that there are some blank spots here. So where I've got two red arrows, there is no signal going to those detectors. And what's interesting here is that I can measure the side scatter from two different lasers. And you can see on the green arrows here, I've got a side scatter measurement from a 488, and over on the left-hand side, I've got a side scatter measurement on the 405. So that's actually a very simple process. I could actually get a side scatter measurement of any laser by simply putting the appropriate bandpass filter into any of these WDM modules. So that's a really neat feature. Here's a slightly different layout, and you can see here that we've split the 375 and the 638 lasers going into these WDM modules. So there's basically, I would say, it's not an infinite number because you have a limited number of lasers and a limited number of detectors, but there's a huge number of combinations that can be made in what I think is pretty clear is the simplest possible layout that you can have for a laser system. So I'm just highlighting there the detector that is split, and here I've again highlighted that I can measure the side scatter from two different lasers. Now, I don't have to. I can put in one or other of these green arrows any appropriate bandpass filter. There's really no limitation to which filters. The only limitation, of course, will be the bands that are actually coming from that laser. So I've just outlined here some of the types of layouts that you can have, and you can see that changing a system is very simple. Now, it is true that you're going to have a fixed laser combination on whatever instrument that you get, but within that fixed laser layout, you have quite a large number of possibilities. And on this slide, for example, with the 405, the 561, the 488, and the 638 laser, I've listed there a lot of the common dyes that you can use. So this really is, I think, a very broad spectrum number of dyes you can use. Now, I think it's only recently that the 375 was added to the CytoFLEX. I haven't used the 375 myself, but I know that Bill Telford and some others have used the 375, and I'll show you some of Bill's data in a moment. But there are some advantages to the 375 laser because it may be even better at exciting some of the these amazing brilliant violet dyes that are now available, and work very well with the 405 laser, and they may well work even better with the 375. Certainly the 375 has an advantage for Herxt and DAPI because it's even more efficient, and I'll show you some data in a moment with the side population. But it's actually fairly good and certainly a lot cheaper alternative to trying to put a true UV laser in the 350, 355 range. And another advantage of that is it doesn't have any high thermal output. And of course, you don't have to deal with the other complications of the 350, 355 lasers with power supplies and high voltage and sheer size. The other thing is that basically it's as good as the 355, almost as good, let me say, as the 355 for most of these dyes. Obviously, having a perfect laser with the absolute right fluorochrome is always better, but it's somewhat impractical to be able to do that. And in the field of flow cytometry, we are almost always compromising on the laser line and the band pass and the dichroics that we use to accommodate our assay design. So these data, excuse me, are showing the 375 laser exciting DAPI, and I think I have a slide in a moment from Bill Telford. I think it's a few slides down, but just to show you a couple of slides that it is indeed possible, depending on the laser combination and the WDM modules that you establish, that you can produce excellent quality multicolor data analysis. And this is showing some 12 color analysis using the UV, true UV laser. So there are advantages and disadvantages with having to set any combination of lasers, but I've highlighted here the yellow laser, and I'm just going to jump down a couple of slides and I'll come back. But the reason I jumped to this 561 is because with DS Red, for example, the 561 is really gives a better signal than the 488. And so that's really a reason for trying to consider, again, depending on the sorts of things that you're running, as to why you might select that yellow laser. But looking at the big picture of this system, taking the rainbow beads, it's pretty clear to me that this system has a great deal of sensitivity and capable of giving excellent resolution on those beads across every spectral component that we're interested in looking at. And looking at particular dyes that are of interest in hematology, in clinical lab, some of the dyes that you see on here show excellent resolution and sensitivity. So I've already shown this slide with DS Red, so I'll jump past it. But I did mention that looking at Herxt and DAPI has some advantages. So here is an example of Herxt and DAPI with the deep UV laser. And this is the side scatter population that Bill Telford did on the CytoFLEX with the 375 nanometer laser to show excellent side scatter resolution. And so that is what I would consider to be a significant advantage of being able to do the 375 nanometer laser. So what would be the take-home messages? So you might be a little surprised at what I think the key take-home messages are from this system. I don't think it's that the system is using APDs, or that the system uses wavelength division multiplexing, or that any of these things that I've shown you are in themselves super special. What I think is super special about this is that the combination of these components, the extreme linearity of these particular APDs, the way they are designed, and the efficiency of the wavelength division multiplexing system, and the efficiency of the light collection, which I really didn't discuss because that is a unique feature of the CytoFLEX. What I understand to be something that's really unique is that because of the linearity of this system, that this will change the way things like compensation can be done. And my understanding of this is that because of the extreme linearity, that compensation in this system can cross different samples and different dyes. And I think that may be unique. And that's not something that has been discussed very much. If this is true, then this changes the way we deal with compensation, because what it means is that we may be able to take a compensation library and do mix and matching for all of the dyes that are run on a system. And that is something we don't consider in most flow cytometers. So that is the end of my presentation. And as I've said here, this opens up the potential of what may be the holy grail of flow cytometry. That is, a generation of instruments that are completely self-calibrated and are able to do this amazing matrix of compensation across a very broad range of dyes. And I guess that my opinion is that the CytoFLEX may well be the beginning of a transformation in how we do flow cytometry. It's not just that this is a tiny little box. It's the combination of these unique tools that are inside this box that I find extremely impressive. And so with that, I'm going to turn over to Judy to see if there are any questions or any discussion that we are going to have.
Thank you for that informative presentation. Before we get started on the question and answer session, I'd like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can, and indeed many have come in so far. Our first question is, what has changed with APDs that has allowed them to work with flow cytometry?
The question is what has changed with APDs that allows them to work with flow cytometry. This is a great question. Like everything, technology has evolved. You know, we all have one of these. Just go back 10 or 15 years and a portable telephone was a shoebox and had very little functionality. And you can ask the question, well, what changed to allow that to happen? A lot of things changed. And the same is true with APDs. The structure, the size, the efficiency of the design, the temperature control, the noise control, the efficiency of getting the signal into the APD, all of those things have changed. So I would say that it's been an evolution over many years of what has actually changed in the APD that has got us to this point where at least one manufacturer, and I guess originally Cytogen, took what might be considered a risk of building a system with APDs, but which I think has turned out to be quite a clever move. So that's the answer to my question. It's a little bit broad, but a lot of changes over time.
Why is WDM more efficient like collection? Okay, so the question is, why is WDM more efficient? Well, I tried to explain how clever WDM was in terms of communication, where you can send 100 or 200 phone conversations down an optical fiber and demux them. That's efficient. One of the reasons why the WDM system in the CytoFLEX is efficient is because it combines the WDM concept with reflection optics. And in reflection optics, you don't lose signal. You keep carrying the signal all the way. So you're not dropping, you're not losing much efficiency. So instead of going through dichroic after dichroic after dichroic and then bandpass, you're really only going through one bandpass filter. So that's one of the reasons why it's more efficient. And I'll hand back to you, Judy. Thank you. Please explain why PMTs have a problem at 750 nanometers.
So the question was, please explain why PMTs have problems at 750 nanometers. Well, it's because of the materials that are used in the elements of the PMT. A PMT works by a photon hitting a material that then emits electrons, and they multiply. And depending upon what that material is made of, the difference in the wavelength of the photons that hits it will determine its efficiency. And it turns out that PMTs work up to about 800 nanometers quite effectively, or not really effectively, but they work okay up to that wavelength. They're obviously much better at the wavelengths that we use in flow cytometry of say 450 to 650 or 700 nanometers. But it's the composition of the materials in the photomultiplier tube that determine its wavelength sensitivity. And I'll hand it back to you, Judy.
Which type of APD is on CytoFLEX SiO2? Which wavelengths are detected into CytoFLEX 300 up to 1100 nanometers?
Thanks, Judy. The question was, what is the nature of the APDs? And I would answer that if I knew, but actually I have no idea. I suspect it's a proprietary piece of information, but I personally do not know.
Do you think of using APD for other cytometers technology?
So the question was, will others use APDs? I guess it's a matter of time. There are a couple of things that are advantageous about APDs. One of them is their cost. They're a tenth the cost of a photomultiplier tube. So the more detectors you want on a system, that should be an economic advantage. But it's tricky using APDs. You have to change a lot of things in how you build the system. It's not just a matter of swapping out the PMT and putting an APD in there. That's not how the CytoFLEX was designed. So my answer is, I would say that other manufacturers would have to be looking at this. I'm certainly experimenting with them in my own lab. So that I'm sure others will be doing the same. Back to you, Judy.
Are APD sensitive to temperature? And if yes, do you think that efficiency could be even better if they are cooled down actively?
So the question is, are APDs sensitive to temperature? And the answer is yes, they are. And it is also true that cooling them can improve them. I don't know the details about how Beckman manage or manipulate their APDs in the system, but in general, the questioner is correct that temperature is usually does have an impact on the noise level of an APD, and cooling is definitely an advantage. Back to you, Judy.
Is there a special limitation for 6 APD by WDM?
So the question is, why are there 6 APDs on the WDM? I have absolutely no idea, but I'm going to make a guess. I would say that it's a matter of physical size and design. 6, it's this, to some extent, the bandpass filter, which is a few millimeters wide, that's going to give some restriction in how many. The second is how far apart the APDs can be mounted. My understanding, although I haven't seen them on the board, but my understanding is the APDs are mounted on a circuit board, and so there's a physical distance between APDs that you have to mount them. The APDs are, I don't know, 5-6 millimeters apart in size. So I suspect that for efficiency, that's the most efficient way of mounting these. And my understanding is that there are 3 banks of APDs on the motherboard, and that they are probably separated physically as closely as an APD can be made. But that's my own personal guess. Maybe someone at Beckman Coulter has a more intelligent answer. Back to you, Judy.
The next person says, I run SSC in linear mode, but some others do it in log mode. Please comment.
So the question is side scatter in linear mode and log mode. Well, this is a digital system. So you have the raw data. You have everything that you need. You don't need to, you can convert this to log data if you want and plot it, but you have all the raw data. So that's the answer to my question, to the question, sorry.
You said that you opened a slot on WDM. Do you know if we could activate them?
I didn't get the question. I didn't get that question. If you can repeat it, please.
You said open slot on WDM. Do you know if we could activate them?
The question was, I mentioned an open slot on the WDM, and can you activate them? Maybe I didn't make myself clear. What I was saying is that I've simply, I showed slots where no bandpass filters were inserted. So no signal, specific signal will be detected on that. So the APD is still active. They're not. There's no requirement for them to be activated. All the APDs are available. I was just indicating that in those 2 slots where those 2 green arrows were on that figure, that there was no bandpass filters there. Back to you, Judy.
Did you try to analyze more than 800 nanometer wavelength on this APD, and did you see a particular benefit compared to PMT in sensitivity, for example?
So the question was, did we go beyond 800 nanometers on the APDs, and will it therefore be more sensitive? And the answer to the first question is no, I have not personally done that. But in theory, the answer is that it should be, because APDs are more sensitive up in the red domain. So I'll hand that back to you with the answer. It should be, absolutely.
With the incorporation of sensitive APDs, does this mean we're no longer dependent on bright fluorescence dyes?
So the question is, if we have APDs, do we no longer dependent on bright fluorescence dyes? And I would say we are always going to be dependent upon bright fluorescent dyes. There's no real easy answer to this question, except that whatever you can do to increase the efficiency of a system should be done. So I would never say just keep going to the most inefficient dyes. I would also say go to the most efficient die is always the best model. So don't depend on the electronics of a technology. Improve your assay, use the best possible dyes that you can. We know that the most efficient way of increasing signal is by having a better fluorochrome. It's not by having a more sensitive technology. More sensitive technologies are great and are really important, but let's not throw away our bright dyes.
Okay, let me know if you can answer this one. How is the dynamic range on the CytoFLEX compared to the Accuri?
So the question is, what is the difference in the dynamic range of the CytoFLEX and the Accuri? I'm not actually certain of the answer to this, but I do believe that the CytoFLEX has a significant dynamic range. I can get that information and provide that to the users, or if it can be added to the website later, I'd be happy to identify the correct technical answer for that, and I would go to a colleague in Beckman Coulter and get those details and provide that for the questioner.
Compensation is also affected by natural autofluorescence of biological samples. How is that library, how will it deal with it?
So the question is, compensation can be impacted by autofluorescence, and how would the system that I mentioned deal with that? Again, I don't know the answer to that. It's going to be dependent on some testing. What I was implying was that if you have a system that is highly linear and reproducibly linear across different instruments, that there ought to be a major advantage in how we deal with compensation. And so I believe that autofluorescence always impacts signals. There are other ways of dealing with autofluorescence, and as many of you know, I'm a proponent of spectral hyperspectral analysis to deal with autofluorescence. That's a completely different issue, but it is one mechanism for dealing with autofluorescence. So I guess it's something that will have to be tested to see what the results bring. Back to you, Judy.
Using time as a parameter, what do you do if there's a blip in the fluorescence? You can always stop the collection or throw out the sample.
Sorry about that delay, but I was waiting for getting control. So the question was using time as a parameter. You can always, you'll always see it if you're running it. The real reason for collecting time is you can always cut it out. If it turns out that there's a blip or a blockage and it's a short period of time where there's a blockage or something else, you can just go in and gate that out on your list mode file, and you save something that might be a very valuable assay. So that's one of the reasons that I suggest that it should be on every system. That if you have an extremely valuable sample and you can't rerun it, and you may be able to save that sample by gating out using time gating. Back to you, Judy.
Have you checked the spillover spreading matrix, SSM, and or the resolution impact matrix, RIM, on the CytoFLEX?
There's a simple answer to that, and the answer is I have not.
You talk about FITC comp of Ocuros CytoFLEX. Did you try to do it now? And according to their respective bandpass filters, does it work well?
I haven't done that across instruments, so I can't personally speak to it, but it is the goal of this technology to essentially create a technology that is so reproducible across instruments that those comps can be carried across. So no, the answer is I have not personally done this, but what I'm trying to explain is that if you can design and build an instrument that is, let's say, so reproducibly designed and built so that the detectors, the optics, have identical features, identical parameters, then this is what I think is one of the big opportunities of a technology. And we know that you just can't do that on most instruments because we're always fiddling with knobs, and we're trying to accommodate our sample to the instrument. Taking one sample from one instrument to another is one of those difficult things that we've struggled for years to try to work out how to compare data from one instrument to another. So the point that I'm trying to make is that I see this as a possibility, that this might be the start of a new way of doing things in flow. Back to you, Judy.
Okay. The next one is demystifying the WDM module. The term WDM leads to a lot of confusion. In my probably naive understanding, there is no real multiplexing or demultiplexing in flow cytometers. There are no discrete laser lines to combine or to divide like in telecommunication networks. Or would you describe the emission of different fluorochromes as multiplexing and the special separation of fluorochromes as demultiplexing? Then the Boulevard Gallios or the POD Austrios would also be WDMs.
So the question about WDMs, what I'm trying to do is explain to you a slightly different way of how the technology is designed. It is not exactly the same as the communication industry. I was using that as an example of how frequency changes are combined and then separated again. What we are talking about on this instrument is a combination of aspects that are WDM-like and utilize a more efficient way of separating the signals that are coming out of initially a single fiber and then being divided into a number of what Beckman Coulter calls WDM modules. Back to you, Judy.
Okay, we have time for one last question, and it is near UV SSC would give even more resolution then, better than violet SSC?
So the question is going down to the near UV, which is described as the 375 nanometer line would give you even better resolution. And in theory, the answer is yes. In theory, it would. That's a fairly simple answer.
I would like to once again thank Dr. J. Paul Robinson for his presentation. Do you have any final comments, Dr. Robinson?
Well, thank you, Judy. The only comments that I have are that it is a lot of fun testing and using new instruments and comparing them with other instruments. And I would say that every instrument has its advantages and disadvantages. And what I've tried to do on this is to outline primarily the advantages of this technology. And I'd be happy to answer questions from people individually. And I'll also point out that very shortly we'll be able to provide a little more detail on some educational videos that we've been making that answer some of these questions in a slightly different way and give you the opportunity of reviewing this material. So thank you for everybody for participating, and I'm happy to answer individual questions. If you send them to me, you can track me down on the Purdue Cytometry list or Google me, and I'm sure you can find me. Thanks very much, and good morning, or is it good afternoon? Good morning to people in California and good afternoon to everybody else.
Thank you again. I would also like to thank our sponsor, Beckman Coulter Life Sciences, for making today's educational webcast possible. Today's webcast will be available for on-demand viewing through June 4th, 2016. You'll receive an email from LabRoots alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. See you next time. Goodbye.